Hello, this is Giovanni Gibilisco, and in the next 20 minutes or so, I'll share with you some of our experiences in tuning applications running on Kubernetes. These are the contents that we will cover. We'll start by identifying some challenges of modern applications for ensuring performance and reliability. We'll then review how our Kubernetes manages container resources and the factors we need to be aware of if we want to ensure high performance and cost efficiency. We will introduce a new approach we implemented at K8s, which leverages machine learning to automate the optimization process, and we will do that with a real-world example. Finally, we will conclude by sharing some takeaways. Before proceeding, let me introduce myself. My name is Giovanni Paolo Gibilisco, and I serve as Head of Engineering at K8s. Okay, let's start with a quick overview of some of the main challenges that comes with the development of modern applications. The advent of agile practices allowed developers to speed up the development cycle, with the goal of getting rapid feedback and iteratively improve applications, though increasing the release frequency. It's now common to see applications or part of them released to production weekly or even daily. At the same time, the underlying frameworks and runtimes, such as the JVM, that are used to build those applications have grown in complexity. The emergence of architectural patterns, such as microservices, have also brought an increase in the number of frameworks and technologies used within a single application. It's now common to see applications composed by tens or even hundreds of services written in different languages and interacting with multiple runtimes and databases. Kubernetes provides a great platform to run such applications, but it has its own complexities. The Kubernetes Failure Stories is a website specifically created to share incident reports in order to allow the community to learn from failures and prevent them from further happening. Many of these stories describe teams struggling with Kubernetes application performance and stability issues, such as unexpected CPU slowdowns and even sudden container terminations. Engineers at Airbnb even got to the point of suggesting that Kubernetes may actually hurt the performance of latency-sensitive applications. But why it's so difficult to manage application performance, stability, and efficiency on Kubernetes? The simple answer is that Kubernetes is a great platform to run containerized applications, but it requires applications to be carefully configured to ensure high performance and stability, as we're going to see. To answer this question, let's now get back to the fundamentals and see how Kubernetes resource management works. To better understand the main parameters that impact Kubernetes application performance, stability, and cost efficiency. Let's go through 5 main key aspects and their implications. The first important concept is resource requests. When a developer defines a pod, she has the possibility to specify resource requests. Those are the amount of CPU and memory the pod, or better, a container within the pod, is guaranteed to get. Kubernetes will schedule the pod on a node where the requested resources are actually available. In this example, pod A requires 2 CPUs and is scheduled on a 4 CPU node. When a new pod B of the same size is created, it can also be scheduled on the same node. This node now has all of its 4 CPUs requested. If a pod C is created, Kubernetes won't schedule it on the same node, as its capacity is full. This means that those numbers the developers specify in the deployment YAML are directly affect the cluster capacity. A strong difference with respect to virtualization and hypervisors is that with Kubernetes, there is no overcommitment on the requests. You cannot request more CPUs than those available in the cluster. Another important aspect is that resource requests are not equal to utilization. If pod requests are much higher than the actual resource usage, you might end up with a cluster that is at full capacity even though its CPU utilization is only 10%. So the takeaway here is that setting proper pod requests is paramount to ensure Kubernetes cost efficiency. The second important concept is resource limits. Resource requests are guaranteed resources that a container will get, but usage can be higher. Resource limits is the mechanism that allows you to define the maximum amount of resources that a container can use. like 2 CPUs or 1 GB of memory. All this is great, but what happens when resource usage hits the limit? Kubernetes treats CPU and memory differently here. When CPU usage approaches the limit, the container gets throttled. This means that the CPU is artificially restricted, and this usually results in application performance issues. Instead, when memory usage hits the limit, the container gets terminated. So there is no application slowdown due to paging or swapping as we had in traditional operating systems. With Kubernetes, your pod will simply disappear, and you may face serious application stability issues. The third effect is about an important and less known effect that CPU limits have on application performance. We have seen that CPU limits cause throttling, and you may think that this happens only when CPU usage hits the limit. Surprisingly, the reality is that CPU throttling starts even when CPU usage is well below the limit. We did quite a bit of research on this aspect in our labs, and found that CPU throttling starts when CPU usage is as low as 30% of the limit. This is due to a particular way CPU limits are implemented at the Linux kernel level. This aggressive CPU throttling has a huge impact on service performance. You can get sudden latency spikes that may breach your SLOs without any apparent reason, even at low CPU usage. Now, some people, including engineers at Buffers, tried to remove CPU limits. What I got was an impressive reduction of service latency. So, is it a good idea to get rid of CPU limits? Apparently not. CPU limits exist to bound the amount of resources a container can consume. This allows many containers to coexist without competing for the same resources. So, if CPU limits are removed, a single runaway container can disrupt the performance and availability of your most critical services. It might also make the kubelet service unresponsive and effectively remove the entire node from the cluster. Using CPU limits is a best practice also recommended by Google. Properly setting your CPU requests and limits is critical to ensure your Kubernetes cluster remains stable and efficient over time. To ease the management of limits and requests for many services, Kubernetes comes with autoscalers. Let's discuss built-in autoscaling capabilities that are often considered as a way to automate this process. In particular, the Vertical Pod Autoscaler, or VPA, provides recommended CPU and memory requests based on the observed pod resource usage. However, our experience with the VPA is mixed. In this example, a Kubernetes microservice is serving a typical diurnal traffic pattern. The top left chart shows the latency of this service and its service level objective, while below you can see the resource request, CPU and memory, and the corresponding resource utilization. We let this service run for a couple of days with some initial resource sizing, then activated the VPA and let it apply the new recommended setting to the pod. It's interesting to see that the VPA immediately decided to reduce the assigned resources. In particular, it cut in half the CPU requests. This is likely due to some apparent over-provisioning of this service, as the CPU utilization was below 50%. However, with the new settings suggested by the VPA, the latency of the microservice skyrocketed, breaching our SLO. What is the lesson learned here? Kubernetes autoscaler, and the VPA in particular, is based on resource usage and does not consider application-level metrics like response time. We need to evaluate the effect of the recommended settings, as they might be somewhat aggressive and cause severe service performance or reliability degradations. As we've seen so far, optimizing microservice applications on Kubernetes is quite a daunting task for developers, SREs, and performance engineers, given the complexity of tuning Kubernetes resources and the many moving parts we have in modern applications. A new approach is required to successfully solve this problem, and this is where machine learning can help. AI and machine learning have revolutionized entire industries, and the good news is that ML can be used also in the performance tuning process. ML can automate the tuning of many parameters we have in the software stack, with the goal of optimize application performance, resiliency, and cost. In this section, I would like to introduce you to this new methodology. The real-world case is about an European leader in accounting, payroll, and business management software, whose Java-based microservice applications are running either on Azure or AWS Kubernetes services. The target system of the optimization is the B2B authorization service running on Azure. It's a business-critical service that interacts with all the applications powering the digital services provided by the company. The challenge of the customer was to avoid overspending and achieve the best cost efficiency possible by enabling development teams to optimize their applications while keeping on releasing application updates required to introduce new business functionalities and align to new regulations. So, what is the goal of this optimization? In this scenario, the goal was to reduce the cloud costs required to run the authentication service on Kubernetes. At the same time, we also wanted to ensure that the service would always meet its reliability targets, which are expressed as latency, throughput, and error rates SLOs. So how can we leverage ML to achieve this high-level business goal? In our optimization methodology, the ML changes the parameters of the system to improve a metric that we have defined. In this case, the goal is simply to optimize the application cost. This is a metric that represents the cost we pay to run the application on the cloud, which depends on the amount of CPU and memory resources allocated to the containers. The ML-powered optimization methodology also allows to set constraints to define which configurations are acceptable. In this case, we state that the system throughput, response times, and error rate should not degrade more than 10% with respect to the baseline. Once we have defined the optimization goal, the next step is to define the parameters of the system that the machine learning can optimize to improve our goal. In this scenario, 9 tunable parameters were considered in total. 4 parameters are related to Kubernetes container sizing, CPU and memory request and limits, which play a big role in the overall service performance, cost, and reliability. And the 5 parameters are related to the JVM, which is the runtime that runs within the container. Here we included parameters like heap size, garbage collector, the size of the regions of the heap, which are important options to improve the performance of Java apps. It's worth noticing that the ML optimizes the full stack by operating on all these 9 parameters at the same time, thereby ensuring that the JVM is optimally configured to run within the chosen container resource sizing. Let's now see how the ML-powered optimization methodology works in practice. The process is fully automated and works in 5 steps. The first step is to apply the new configurations suggested by the ML algorithm to our target system. This is typically done leveraging Kubernetes APIs to set the new value to the parameters, for example, the CPU requests. The second step is to apply a workload to the target system in order to assess the performance of the new configuration. This is usually done by leveraging performance testing tools. In this case, we use a JMeter test that was already available to stress the application with a realistic workload. The third step is to collect KPIs related to the target system. The typical approach here is to leverage observability tools. In this case, we integrated Elastic APM, which is the monitoring solution used by the customer. The fourth step is to analyze the result of the performance test and assign a score based on the specific goal that we have defined. In this case, the score is simply the cost of running the application containers, considering the prices of Azure Cloud. The last step is where the machine learning kicks in by taking the score of the tested configuration as input and producing as an output the most promising configuration to be tested in the next iteration. In a relatively short amount of time, the ML algorithm learns the dependencies between the configuration parameters and the system behavior, though identifying better and better configurations. It's worth noticing that the whole optimization process becomes completely automated. So, what are we getting as an output of the ML-based optimization? The main result is the best configuration of the software stack parameters that maximize or minimize the goal we have defined. These parameters can be then applied in production environments. But the value this methodology can bring is actually much higher. ML will evaluate many different configurations of the system, which can reveal important insights about the overall system behavior in terms of other KPIs like cost, performance, or resiliency. This supports performance engineers and developers in their decision on how to best configure their application to maximize the specific goals. So, to assess the performance and cost efficiency of a new configuration suggested by the ML optimizer, we stress the system with a load test. Here you can see the load test scenario that we use. It was designed according to the performance engineering best practices. The traffic pattern mimicked the behavior seen in production, including API call distribution and think times. Before looking at the results, it's worth commenting on how the application was initially configured by the customer. We call this the baseline configuration. Let's look at the Kubernetes settings first. The container powering the application was configured with resource requests of 1.5 CPUs and 3.42 GB of memory. The team also specified the resource limits of 2 CPUs and 4.39 GB of memory. Remember, the requests are the guaranteed resource that Kubernetes will use for scheduling and capacity management of the cluster. In this case, the requests are lower than the limits. This is a common approach to guarantee resources for the application to run properly, but at the same time allow for some room for unexpected growth. Besides looking at the container settings, it's important to also see how the application runtime is configured. The runtime is what ultimately powers our application, and for Java apps, we know that JVM settings play a big role in app performance, but the same happens for Golang applications, for example. The JVM was configured with a minimum heap of half a gig and a max heap of 4 GB. Notice that the max heap is higher than the memory requests, which means that the JVM can use more memory than the amount requested. As we're going to see, this configuration will have an impact on how the application behaves under load and the associated resiliency and costs. It's worth noticing that the customer also defined autoscaling policies for this application, leveraging the K8s autoscaling project for Kubernetes. In their environment, both CPU and memory were defined as scalars, with a triggering threshold of 70% and 90% utilization respectively. What is important to keep in mind is that such utilization percentage are related to the resource request, not limits. So, as you can see in the diagram on the right, an action to scale out the application will happen, for example, when the CPU usage will go above 1 core. Okay, we've covered how the application is configured. Let's now look at the behavior of the application when subject to the load test we've shown before, with the baseline configuration. In this chart, you can see the application throughput, response time, and the number of replicas that were created by the autoscalers. Two facts are important to notice. When the load increases, the autoscaler triggers a scale-out event, which creates a new replica. This event causes a big spike on response time, which impacts service reliability and performance. This is due to the high CPU usage and throttling during the JVM startup. Where the load drops, the number of replicas does not scale down, despite the container CPU usage is idle. It's interesting to understand why this is happening. This is caused by the configuration of the container resource, the JVM running inside, and the autoscaler policies, in particular for the memory resource. The autoscaler in this case is not scaling down because the memory usage of the container is higher than the configured threshold of 70% usage with respect to the memory requests. This might be due to the JVM max heap being higher than the memory request we've seen before, but it may also be due to a change in the application memory footprint, for example, due to a new application release. This effect clearly impacts the cloud bill as more instances are up and running than required, but shows that configuring Kubernetes apps for reliability and cost efficiency is actually a tricky process. Let's now have a look at the best configuration identified by ML with respect to the defined cost efficiency goal. This was found at experiment number 34 after about 19 hours, and almost half the cost of running the application with respect to the baseline. First of all, it's interesting to notice how our ML-based optimization increased both memory and CPU requests and limits, which is not at all obvious and may seem at first counterintuitive, especially as Kubernetes is often considered well-suited for small and highly scalable applications. The other notable changes are related to the JVM options. The max heap size was increased by 20% and is now well within the container memory request, which was increased to 5 GB. The min heap size has also been adjusted to be almost equal to the max heap, which is a configuration that can avoid garbage collection cycles, especially in the startup phase of JVM. So let's now see how the application performs with the new configuration identified by ML and how it compares with respect to the baseline. There are two important differences here. Response time always remains within the SLO and there are no more peaks. So this configuration not only improves on cost, but it's also beneficial in terms of performance and resilience. Autoscaling is not triggered in this configuration, as the full load is sustained by just one pod. This is clearly beneficial in terms of cost. Let's also compare in detail the best configuration with respect to the baseline. Here we can notice that the pod is significantly larger in terms of both CPU and memory, especially for the requests. This configuration has the effect of triggering the autoscaler less often, as we have seen, but interestingly and somewhat counterintuitively, while this implies a kind of a fixed cost, considering the prices of the container resource, it turns out being much cheaper than a configuration where autoscaling is triggered. And this also avoids performance issues. The container and runtime configuration are now better aligned. The JVM max heap is now below the memory request and has a beneficial effect, as it also enables the scale down of the application, should the scaling be triggered by higher loads. Let's now have a look at another configuration found by ML at experiment number 14, after about 8 hours of automated optimization. We label this configuration high reliability, for a reason that will be clear in a minute. The score for this configuration, while not as good as the best configuration, also provided about 60% cost reduction. So this can be considered also an interesting configuration with respect to the cost efficiency goal. As regards the parameters, what is worth noticing is that this time ML picked settings that significantly change the shape of the container. It now has a much smaller CPU request with respect to the baseline, but the memory is still pretty large, which is pretty interesting. The JVM options were also changed. In particular, the garbage collector was switched to parallel, which is a collector that can be much more efficient on the use of CPU and memory. Let's compare the behavior of this configuration with respect to the baseline. There are two important differences here. The peak on the response time upon the scaling out is significantly lower. It is still higher than the response time SLO, however the peak is less than half the value of the baseline configuration. This clearly improves the service resilience. Autoscaling works properly. After the high load phase, replicas are scaled back to 1. This behavior is what we expect from an autoscaling system that works properly. Notice the response time peaks could also be further reduced. It would simply be a matter of creating a new optimization with the goal of minimizing the response time metric instead of the application cost. Let's now also compare in detail the high resilience configuration with respect to the baseline. Quite interestingly, this configuration has a higher memory request and lower CPU requests, but higher limits, than the baseline. As you may remember, the lowest cost configuration instead had a higher CPU request than the baseline. Without getting into much details in the analysis of this specific configuration, what these results show is that as the optimization goal changes, CPU and memory requests and limits may need to be increased or decreased, and that multiple parameters at Kubernetes and JVM levels also need to be tuned accordingly. This is a clear confirmation of the perceived complexity of tuning Kubernetes microservices application. As here we're just discussing one microservice out of hundreds or more of today's applications. There are many other interesting configurations found by ML that we would like to discuss, but I think it's time to conclude with our takeaways. Our first takeaway is that when tuning modern applications, the interplay between different application layers and technologies require tuning the full stack configuration to make sure that both the optimization goal and SLOs are matched, as we've seen in our real-world example. A second takeaway is that the complexity of this application under various workloads and in a context of frequent releases with agile practices requires a continuous performance tuning process. Developers cannot simply rely on manual tuning or utilization-based autoscaling mechanisms. Finally, in order to explore the vastness of the space of possible configuration in a cost and time-efficient way, it's mandatory to leverage ML-based methods that can automatically converge to optimal configuration within hours without requiring deep knowledge of all the underlying technologies. Many thanks for your time. I hope you enjoyed the talk. Please reach out to me if you have found this talk interesting. I would love to share more details and hear your Kubernetes challenges. Bye-bye!